Hello everyone, welcome. In this video we are going to discuss about projectile motion simulation part 2. So in this we are going to discuss two aspects. One is under what condition the effect of air resistance can be neglected. So air resistance is always there. Having no resistance of air is ideal situation. So under what condition this ideal situation can be a good approximation to study real life example. So that's one thing. The second one is when the particle is projected in ideal situation, what kind of vectors can be used to describe the motion like velocity vector, acceleration vector and force vector, and how are they going to change? What are they changing and how are they going to be involved? So this is another aspect we want to see that. So we want to understand the vectorial description of the projectile motion. That's the second part. Okay, let's start. So as usual on the left hand side at the bottom you see you have the speed of projection which can vary from 0 to 30 meter per second. Let's take somewhere in the middle, let's say 15 meter per second, and similarly this angular projection can be varied from 25 degrees to 90 degrees. Let's take 45 degrees as we discussed already. At 45 degrees angular projection the horizontal range would be maximum for a given speed of projection. We have already seen it. So now what we do, we go to the right hand side. We have one parameter which is the size, diameter of the cannonball, which can vary from 0.1 meter to 1 meter. And also we have mass of the cannonball, varying from 1 kg to 10 kg. So I'll take four situations here. One is the least size and least mass. And then we go for highest size and highest mass. Second situation. Third situation, highest size and least mass. And then fourth situation, least size and highest mass. In these four cases, we want to understand how the projectile will be moving when air resistance is present. So we will always compare it with the ideal situation where air resistance is 0. So which is going to be closest to that ideal situation that we want to understand. First thing is when you go for any size, when there is no air resistance, path is going to be the same. So you take any size, you're going to have the same path, right? You take 0.1 diameter, same path. You can't even say the size of it, or maybe you can take 1 meter and project it is going to produce the same path. You take 1 kg mass and project it, there's no difference, it will continue in the same path. Or you take 10 kg mass, you project it, it is going to continue in the same path. So path will not be affected in terms of the diameter of the cannonball and mass of the cannonball. Okay, that is when ideal situation, that is when air resistance is neglected. But when air resistance is present, which is going to be closest to this ideal situation, that's what we want to understand. So let's go with the air resistance included with the drag coefficient 0.47. So let's go with the first situation where you have the least mass and least size and then project it. You see that it is going to go and fall somewhere here. Okay, that is case 1, least size and least mass. Then you go for maximum size and least mass and project it. That's pretty bad. So you see that the deviation is pretty high in the second case. Least size, least mass and highest size is going to have a very different path compared to the ideal situation where air resistance was not at all there. Okay, let's go for the third situation where you have least size and highest mass. Let's consider that. Okay, order could be anything. Let's see what would happen. That seems very close to that ideal situation. When you have least size and highest mass, you see that the path is very close to that blue line, almost matching, of course slightly less, slightly undershooting, but very close to it. Okay, then final situation, you have highest size and highest mass and then you project it, you see that it is somewhere in the middle. So in all these, worst case scenario is this, that corresponds to what? Highest size and least mass. Highest size and least mass will cause a lot of variation. And then what is the best one? Having a least size and highest mass. That's going to be the best one, which is going to be very very close to their ideal situation. So when can you neglect the effect of air resistance? And that is this one. When you have a very very small size, almost like a particle. That's why we study particle mechanics, where air resistance can be neglected. When the size is very very small and a lot of mass is concentrated in that, that's where the effect of air resistance can be neglected. So that's one part we have analyzed it. Okay, let's close this air resistance effect. Come back to any median well. When the air resistance is not there, size and mass will not be affecting the path anyway. Now let's focus on the second part, how these vectors would change. Now remember, what is vector quantity? It's a physical quantity. It has got both magnitude as well as direction. So the vectors that we're going to discuss is a velocity vector with green line, green arrow, acceleration vector with yellow arrow, and force vector with a black color arrow. So whenever we represent a vector with arrow, so we look at two things. The direction of the arrow is the direction of vector, and the length of the arrow is proportional to magnitude of the vector. So those two things we will take into consideration. So first let's go with the velocity vector and see how it is going to vary as it is projected. Look at the entire projectile motion. This is going to be a parabolic path. It went very fast, so let us slow down. Look at it in slow motion. Again, let's project it and see how it is going to go. I go in slow motion. Now you see it's going, it is continuously turning clockwise. So, and you also observe very carefully, length of the arrow is continuously decreasing up to the highest point, and after that the length of the arrow is continuously increasing. So the length of the arrow represents speed, magnitude of velocity vector. So speed is decreasing up to the highest point. At the highest point it is having the least speed. That's where you have the least length of the arrow. And then after that velocity magnitude is increasing. And the direction is continuously turning clockwise. Now let's look at it in stop and go motion, so that we can understand the arrow direction as well as magnitude at every moment. Shoot. Let's go one by one. See how the arrow is changing. At every moment arrow is tangential to the path. So velocity vector is always tangential to the path. That is one important aspect you should remember. The velocity vector is always tangential to the path. And you can see the length of the arrow is continuously decreasing as it is going up and turning clockwise. As it reaches to the highest point, where is it reaching? The dot, blue dot at the top, and that's a green dot. Now it is at the highest point, and you see that at the highest point velocity vector is horizontal. So this is another important observation. At the highest point velocity vector is completely oriented along horizontal direction. That's very important. Velocity vector is horizontal at the highest point. Okay, go on ahead. As it moves further down, it is turning, and you see that the length of the arrow is continuously increasing afterwards. So speed is decreasing up to the highest point, and then after that it is increasing till the bottom. So that's one aspect. Now let's look at the velocity vector in terms of the components. We can resolve any vector into two mutually perpendicular components in that plane. Let's take horizontal component and then vertical component. Let's resolve this velocity vector into horizontal component as well as vertical component and see what would happen to these components individually. You see that vertical component is changing. Initially vertical component is directed upwards, decreases to 0 at the highest point, and after that it is turning down. So let's look at it at any moment. You see, as you are going, vertical component is decreasing. Vertical component is decreasing. You see that it is becoming 0. At the highest point you will have only horizontal component. After that the vertical component is increasing in the downward direction. So it reaches to the bottom there. Once again let us shoot and focus on horizontal component now. So let's take the length of the horizontal component. Let's calculate the length of it, because length of the arrow should be proportional to the magnitude of the vector, right? So it's approximately 5 meters. Let us shoot it to some other position and then analyze it. Check what happens to the horizontal component of velocity vector. Is it the same? Yes, it is the same. Even at the highest point also it will have the same. It has just gone beyond the highest point, but the horizontal component is not changing. You see that it is the same length. Throughout the motion, horizontal component is not changing. Horizontal component of velocity vector is constant. Horizontal component of velocity vector is constant. So that's one more important aspect. So if you look at the component wise, horizontal component is continuously the same one. It's uniform throughout the motion or constant throughout the motion. But the vertical component was initially upwards. It decreases to 0 till the highest point, and after that it turns down and increases in opposite direction. So that's what we have it. So whenever velocity changes, you should know that there must be acceleration, right? What acceleration is causing it to change? What is acceleration? You know that it is acceleration due to gravity. Earth is pulling it down due to gravitational force of attraction between Earth and the projectile. The projectile is being pulled down vertically downwards. Let's look at the acceleration as well as velocity vector and see how they change. Now you focus at any moment. You see this yellow line corresponds to acceleration, and you see it is vertically downwards, and initially vertical velocity is upwards, and whenever velocity is opposite to acceleration, right, you see that the magnitude of velocity vector will change, decrease. You see, as long as acceleration is opposite to velocity vector, the component will decrease. Vertical component is decreasing because it's opposite to acceleration, but there is no change in horizontal velocity because there is no horizontal acceleration. No horizontal acceleration meaning no change in horizontal velocity. But there is acceleration vertically, so velocity is decreasing because velocity is opposite to acceleration until it reaches to the highest point. At the highest point, vertical velocity becomes 0. So there is only downward acceleration. What is the acceleration of the projectile? It is vertically downward, that is due to acceleration due to gravity. So the direction of acceleration vector is not changing. Magnitude of acceleration vector is not changing throughout the motion. And here horizontal component of velocity vector is not changing. Only the vertical component of velocity vector is changing both in magnitude as well as in direction. Up to the highest point it has got upward velocity, and then after that it is going to have a downward velocity. Okay, when you have acceleration, you must have the cause of it. What is the cause of acceleration? That's a force. That force is a force due to gravity. So let's understand the gravitational force, all right, and see how the gravitational force is acting. And you see that gravitational force is vertically downwards. This vertical gravitational force, which is represented as a black arrow, is producing this vertical acceleration, which is represented as yellow arrow, and that is changing only that vertical velocity, which is green line in vertical direction. But in horizontal direction, there is no force acting on the projectile, and so there is no horizontal acceleration. When there is no horizontal acceleration, there is no horizontal change in velocity. So that's what you have here. So in mechanics, we discuss mechanics into two parts. One is the kinematics and the other one is dynamics. In kinematics, we just describe the motion without actually understanding or trying to understand the cause of it. Just try to understand the motion, describe the motion in mathematical way, graphically, vectorially, and then in terms of the equations. So how velocity is changing, how it is related to acceleration, how position is changing, and all that. So here we are looking at how velocity vector is changing because of acceleration. And then when you go back to why it is happening, that becomes dynamics, and that is happening because of gravitational force. So force causes acceleration and acceleration causes change in velocity. So there is a cause effect relation if you observe it carefully. Force causes acceleration, that's what Newton's law says. Net force acting on the body produces acceleration, and that acceleration is causing change in velocity. So that's how we need to understand it. So with that, I'll close here. I hope you understand the vectorial representation and also the idealization of air drag being neglected. So those two things I wanted to discuss here. So with that, I'll close here. Until next time, goodbye. Thank you.